Hello class, welcome to Advanced Engineering Physics or ES12, and today's topic is pressure. So last time we talked about specific volume and density, and now let's talk about pressure. So when dealing with fluids and gases, we ordinarily speak of pressure, and in solid we speak on stresses. No? But the pressure in a fluid at rest at a given point is the same in all directions. So for that, let's define pressure first for more information. So pressure is defined as the force per unit area measured in Pascal, where Pascal is defined as 1 Newton per square meter. Or more specifically, pressure, if we denote in this equation, so let's say delta A or change in area is a small area, while the delta A prime is the smallest area over which we can consider the fluid a continuum. And the delta F with the subscript of N is the components of the force normal or the normal force. To the delta A, we define pressure or P or denoted as P as pressure is the limit of the change in the normal force over the change in area, where the change in area of the small area to the smallest area. So that would be this equation. So where the lower limit corresponds to the sizes as mentioned for the specific volume. So pressure at a point in a fluid is in equilibrium is the same in all directions. In a viscous fluid, that would be different case if it is viscous. So when we say viscous, mga sticky na siya na fluid na. The variation in the state of stress with orientation becomes an important consideration. So munang lahi na siya pod na we will talk about that on the later topics, no? Deeper na siya when we say viscous fluid. So let's define more on pressure. So absolute pressure is measured from the datum of absolute zero pressure or perfect vacuum. The atmospheric pressure is pressure caused by weight of the atmosphere. And we have the gauge pressure is the pressure difference between the system and the atmospheric pressure. An ordinary pressure gauge will have a reading of 0. This simply means that there is no excess pressure other than the atmospheric pressure. So this is the difference between the system and the atmospheric pressure. Next, we define vacuum pressure is a pressure which is significantly lower than atmospheric pressure. We also have critical pressure is the minimum pressure needed to liquefy gas at its critical temperature. We have here the formula for pressure. We have pressure is equal to force over area as defined earlier. No, it is the force per area. And we have the absolute pressure is equal to the atmospheric pressure plus the pressure gauge. And we have the absolute pressure is just equal to the atmospheric pressure minus the vacuum pressure, where P gauge is the gauge pressure, the P absolute is the absolute pressure, the P, the subscript of ATM is the atmospheric pressure, and the P vacuum is the vacuum pressure. So we have here its unit. So we have Pascal, where 1 Pascal is just equal to Newton per meter squared, as mentioned earlier. And we have here bar. 1 bar is equal to the 10 to the 5th Pascal, or just equal to 0.1 megapascal. And we have the standard atmosphere, which is equal to 101,325 Pascal, or just equal to 14.696 pounds feet per inch squared. No? As I mentioned earlier, the unit of pressure in the international system is force per area, or a force of 1 Newton acting on a square meter area, which is called Pascal. So that's it. We have two other units that are widely used also to continue. So this is the bar and the standard atmosphere, which is the standard atmosphere is slightly larger than the bar. So we have here the units in ATM, or the atmosphere. One atmospheric pressure is just equal to 101,225 Pascal, or 101.325 kilopascal. We have 1.013 bar, or 1.013 times 10 to the power of 6 dynes per centimeter squared. We also have 14.7 pounds per inch squared, or 760 millimeters of mercury. We also have the 60 torr, and we have the 29.92 inch of mercury. So that's our different units using at atmospheric pressure. 1 atmosphere. So we have here, consider a gas contained in a cylinder. So here we have fitted in a movable piston. So this is a movable piston as shown. So the pressure exerted by the gas on all of its boundaries is the same, assuming that the gas is in equilibrium state. No? So every time the force was been exerted, so the pressure is the same in all points, given that it is in equilibrium state. No? So on piston, since there must be a balance of forces for the piston to remain stationary. Thus, the product of the pressure and the movable piston area must be equal to the external force, which is this one. Is now changed in either direction, so the grasp pressure inside must accordingly adjust with appropriate movement of the piston. Now, to establish a force balance at a new equilibrium state. So we have also here another example. If the gas in the cylinder is heated, so as the temperature rises, the pressure rises. No? So the pressure remains equal to whatever value is required by the external force. No? So from this one, we have this illustration. So this is in equilibrium. So the pressure exerted on the piston is the same through all points or all sides, no? Which is also equal to the force exerted from the outside, no? So the pressure multiplied by the area of the piston is just equal for the external force. Now let's have an example. So the hydraulic piston or cylinder system shown in the figure, so we have here, has a cylinder diameter of 0.1 meters with a piston and rod mass of 25 kilograms. The rod has a diameter of 0.01 meter with an outside atmospheric pressure of 101 kilopascal. The inside hydraulic fluid pressure is 250 kilopascal. How large a force can the rod push within the upward direction? No? So how large a force can the rod push within the upward direction? So let's start with the given. And we have the diameter of the cylinder is equal to 0.1 meter. We also have the mass of the rod, which is equal to the 25 kilograms. We also have the diameter of the rod is equal to 0.01 meter. We also have the pressure, the outside atomic pressure is equals to 101 kilopascal. We also have the pressure of the cylinder as equal to 250 kilopascal. and the what is asked is the force of the rod. No? So we know that the summation of forces in a system, or the net force, is just equal mass times acceleration is equals to 0, because we assume that it is a static balance of forces on the piston, and we say that the summation of forces in the system is just equal to 0. So the net force is just equal to the force exerted by the cylinder and the force exerted from the outside. We also have the force of the rod, which is what is asked for this problem, and we also have the force of the piston. No? So we have both the pressure from the cylinder, we have the pressure from the outside, and we also have the mass of the piston. And we know that the pressure is just equal to force over the area. And so we get the force is just equal to the pressure multiplied by the area. So from there, we know that the force of the rod is what is asked. So we got the force is just equal to the force of the cylinder minus the force of the outside minus the force from the piston. So we get the force in this equation. So we get the pressure of the cylinder multiplied by the area of the cylinder minus the atmospheric pressure outside multiplied by the area of the cylinder minus the area of the rod minus the mass of the piston times the gravity. So we get the for the area of the cylinder and the rod, we are given with the diameter of this. So we solve first the area. So the area that we are referring to is the cross-sectional area of the cylinder and also of the rod. So the cross-sectional area of the cylinder is just equal to the area of a circle if cut to the parallel to the circular base. So we get the area of the cylinder is equal to pi r squared, I mean the cross-sectional area, the area of the circle, and we are given with the diameters of that, so we can use the formula pi d squared over 4, where d is the diameter. So we now have the area of the cylinder is just equal to pi multiplied by the diameter of 0.1 meter squared over 4, and we get 7.854 times 10 to the negative 3 meter squared. Okay, and now let's also get the area of the rod, the cross-sectional area of the rod. So still it is circle in the cross-sectional area is the circle, so we have pi r squared, which is also equal to pi multiplied by diameter squared over 4. So we get pi multiplied by 0.01 meter squared over 4, and we get the area of the cross-sectional area of the rod as 78.5398 times 10 to the negative 6 m squared. So we just use this what we get into the formula. So we have here the we know that the pressure of the cylinder is 250 kilopascal, so that would be 250 times 10 to the power of 3 pascal, and multiplied by the area of the cylinder is 7.854 times 10 to the negative 3 meter squared minus
the pressure from the outside is equal to 101 times 10 to the power of 3 Pascal, multiplied by the area of the cylinder is 7.854 times 10 to the negative 3 meters squared, minus the area of the rod is 78.5398 times 10 to the negative 6 meters squared, minus the mass of the piston is 25 kilograms, multiplied by the gravity is 9.81 meters per second squared. So from there we get 250 times 10 to the power of 3 Pascal, multiplied by 7.854 times 10 to the negative 3 meters squared. That would be equal to 1963.5 Pascal multiplied by meter squared, minus we have 101 point times 10 to the power of 3 multiplied by 7.854 times 10 to the negative 3 minus 78.5398 times 10 to the negative 6. That would be equal to 785.3215 Pascal meter squared, minus we have 25 times 9.81 is equal to 245.25 kilograms meters per second squared. And we know that Pascal is just equal to Newton per meter squared, and that Newton is just equal to kilogram meters per second squared. So we can say that we have 19.60 1963.5 minus 785.3215 is equal to 1178.1785. That would be Newton per meter squared multiplied by m squared, so that would be cancelled, so that would be Newton, minus 245.25 Newton. Again, kilograms multiplied by meter per second squared is just equal to Newton, so that would be 245.25 is equals to 932.9285 Newton. So the force that we are referring to, or what is asked, is equal to 932.9285 Newton.
So that would be the solution for the problem. So I just attach this one for those in case na diretso naman kita sa answer. So we have here the solution. And then let's talk about the force acting downward at the bottom of the column. So consider a column of fluid of height h, now standing above point B in the manometer. So where M is the mass of the fluid column and A is its cross-sectional area, and this one, the small letter P, is the density. No, so this force must be equal to by the upward force at the bottom of the column, which the pressure at B multiplied by area. No? So we have here the atmospheric pressure multiplied by the area plus the mass of the liquid multiplied by the gravity, which is 9.81 meters per second squared, is just equal to the atmospheric pressure multiplied by the area plus the density multiplied by the area multiplied by the gravity and multiplied by the height. So it's just equal. Na? So So therefore, since points A and B are in the same elevation in columns of the same fluid, so their pressure must be equal to 0. No? Again, pressures from the pressure of liquid varies as the depth of the cylinder or the material you used is varies also, no? So it varies through the depth of the container, no? So we have here at point A and point B, so they have the same measure with the same liquid that was used. So we can say that it must be equal to 0. So the overall, we have here the pressure at B minus the atmospheric pressure is just equal to the density of the water multiplied by the gravity and the height. No? So let's have here the another equation from that one. So we can say that the summation of pressure is just equal to the pressure of the fluid minus the atmospheric pressure is just equal to the density of the water multiplied by the gravity and the height. Now, since this is the same, so we consider this one, this system, and then therefore the summation of the pressure is just equal to the pressure of the fluid minus the atmospheric pressure, which is just equal to the pressure exerted here. No? So next, consider the barometer. We have here the illustration used to measure the atmospheric pressure as shown in this figure. So since there is a near vacuum in a closed tube, so as you can see, it is closed above the vertical column of fluids. So usually it is in mercury. So we say it is in mercury. So the height of the fluid column gives the atmospheric pressure directly from the previous equation. So we can say that the atmospheric pressure is just equal to the density of mercury multiplied by its gravity and then the height. No? So let's have here an example. A mercury barometer located in a room at 25 degrees Celsius has a height of 750 millimeter. What is the atmospheric pressure in kilopascal? So we are given with since we use a mercury, so we need the value for its density. So based on this table, we have here the values or the properties of some liquids at 25 degrees Celsius, and we see here the mercury is equal to 13,580. So you may base on this table for the value of density if ever the constant value was not given in the problem. No? So from there, let's solve. So we have the given. So may hint na tayo na it is at a room temperature of 25 degrees Celsius. And we have the height is given, which is 750 millimeter. So what is asked? So we're going to find the atmospheric pressure in kilopascal, and based on the table, we get the data of its density or the value of density as 13,580 kilograms per meter cube. So let's start with this formula. So we know that the atmospheric pressure is just equal to the density multiplied by the gravity and the height. No? So we have atmospheric pressure is just equal to the density is 13,580 kilograms per meter cube. And the gravity is 9.81 meters per second squared. And we have the height given, which is 750 times 10 to the negative 3 because it is in terms of meter na. No? So this one, the given is in millimeter. So we need to convert it in meters, so we use it times 10 to the negative 3. So from there, we get, so multiplied that one, so we get the product of 99,914.85. So from here, we can cancel the meter. And then, so ang nabilin is meter squared. So we have kilograms per meter squared, then multiplied by meters per second squared. No? So we have 99,914.85. We know that kilograms meters per second squared is just equal to Newton. So Newton over meter squared. And we know that Newton per meter squared is just equal to Pascal. No? So we say that we have the final answer as 99.914 kilopascal. So we, again, it's in kilo. So we have here the scientific notation as 99.914, no? Because it is in kilo na. So again, Newton per meter squared is just equal to Pascal. So we have the final answer as that one. Okay, so that's it for this topic, and I will just attach more sample problems from videos that are available online. Next topic is energy, so see you at the next topic.